Good morning, everyone. In our discussion on Newton's laws today, we are going to look at the final matric exam paper of 2017, 2018, and 2019, and we're going to look at question 2 every time because question 2 is usually the question on Newton's laws. Now let's start with this question from 2017. An 8-kilogram block P is being pulled by a constant force up a rough inclined plane at an angle of 30 to the horizontal at a constant speed. Now from this, we need to take the fact that it's a rough surface, and that immediately is going to tell me there's a kinetic frictional force working there. And then there's definitely a reason why that constant speed over there is printed in capital letters. That is going to show you how to approach this question. Which law of Newton are you supposed to use? Now, if it's constant speed, that means I'm working with Newton's first law, and I will start with F net being equal to 0. Now, the first question here is just to draw a labeled free body diagram for block P. Now, you've got the normal force, the frictional force, and the applied force, and now we need gravity. Now for gravity, you can draw either the whole gravity like this, or you can substitute that for the two components. Just remember that you are never supposed to have the gravitational force and the components on one drawing. If you have them both, then you're actually drawing that force twice and you will lose that mark. In 2.1.3, they tell us that the kinetic frictional force between the block and the surface of this inclined plane is 20,37. So we have the value for our kinetic frictional force. And now they ask us to calculate the magnitude of that force F. Now remember, for magnitude, I don't have to include direction. Now here I'm going to start off with F net equals m times a. That is going to be 0. Now let's look at the forces. F net is the sum of all the forces. Now, I don't have to worry about the forces that's perpendicular to the movement. They cancel out. They make a 0 net force. So we are only concerned with the forces in the direction of movement. And that is the direction of movement. So that is going to be my positive direction. So now F is going to be a force in the positive direction, and gravity and also that parallel component are going to be in the negative direction. And then we just need to substitute. Now for gravity parallel, that is going to be 8 times 9,8, the whole gravity, and then times sine of that bottom angle. And that bottom angle was 30. And that gave me 0. And then you had to solve for F. And then F was just 59,57 Newton. Now in 2.1.4, we have the most dangerous type of question, and that is when they change something halfway through. Now they tell you that F is now removed. Immediately everything is changing, and you have to be very careful. What do you use that's going to stay the same and what is changing? Now F is removed, so there's no force upwards, and since the block is now accelerating down the plane, friction is going to be up, and we have a new positive direction. So now we need to look at the forces again. This time we've got a frictional force upwards because we are accelerating down the plane. And we still got the normal force and the gravity as before. And they tell us that the frictional force is remaining 20,37. And now they ask us to calculate the magnitude of that acceleration of the block. If they want the acceleration, that's all about Newton's second law, and I'm definitely going to start this question with F net is equal to m times a. Now m in this instance, 8, and the acceleration is the purpose of my calculation. Now let's talk about F net. In this one, the perpendicular forces are once again going to cancel out, and I'm going to look at the forces in the direction of movement. And now, since that object is moving down, that is now going to be my positive direction. So here I'm going to say F gravity parallel, which is in the positive direction, plus the the friction that is in the negative direction will now be equal to m times a. And now replacing that for gravity parallel, that will be the whole gravity, a times 9, 8. For a parallel component, I have to multiply that by sine of that bottom angle of 30, minus, and then the frictional force, they told us it's still 20,37, and that gives you 8a. And then we can just solve for a, and we end up with 2,35. Since it's acceleration, that will be meters per second square, and we don't need a direction. In 2018, they told us that a block of mass 8 kilograms is placed on a rough horizontal surface, once again telling us there's going to be some frictional force over there. And then the 8 kilogram block, which is connected to a 2 kilogram block by means of a light inextensible string passing over a light frictionless pulley, starts sliding from point A as shown. So it is starting from point A and moving towards the edge of this table. And now they ask us to draw a free body diagram, and only for the 8 kilogram block. So for that 8 kilogram block, and then we've got this tension in this rope. And since that is working at an angle, I can either draw the force or I can draw the components. Just don't do both. So either the force or the component. So let's choose the component. So that will be Ty and a T in the X direction. In 2.3.1, they tell us that when the block reaches point B, the angle between the string and the horizontal is 15 degrees, and the acceleration of the system is 1,32 meters per second square. Now, very important, the word acceleration. That is going to tell us which law of Newton is applied here. Now, acceleration, that will immediately tell me I'm working with Newton's second law, and there is a net force present. So now if they ask us in 2.3.1, give a reason why the system is not in equilibrium. Equilibrium means that the net force on that object is 0. And it is not true here. So the reason will be the fact that the system accelerates and the net force is therefore not equal to 0. In 2.3.2, they ask us to use that 2 kilogram mass to calculate the tension in the string. The tension over here and the tension over there are going to be exactly the same. But at the moment, we're only focusing on that 2 kilogram. So let's go and draw a force diagram for that 2 kilogram object. So you've got the tension working upwards, and you've also got your gravity working downwards. And since this system is accelerating, they gave us the acceleration downwards as 1,32 meters per second square. This is going to be my positive direction. So here I'm going to start with F net is equal to m times a. And now for F net, since we're using downwards as positive, gravity is going to be a positive value and T is going to be a negative force. So here we have gravity plus minus T, and that is going to be equal to 2 times 1,3. And gravity here, 2 times 9,8. And then you have to solve for T, and that is 16,96 Newton. In 2.3.3, they ask us to calculate the kinetic frictional force between that 8 kilogram block and the horizontal surface. So let's look at the forces first. Now we've calculated the tension in the rope there, and that tension was 16,96 Newton. And remember, in a rope, the tension on both sides are going to be equal. And the tension on that side is also going to be 16,96 Newton. Now we have to calculate the kinetic frictional force between the 8 kilogram block and the horizontal surface. So when we look at that free body diagram again, that's going to show us all the forces working on this object.
And now remember, we are accelerating. And if you're accelerating, it means we are working with Newton's second law. And for that, we will start with F net equals m times a. I don't have to look at up and down because they are cancelling out. This object is not moving in that direction. I have to focus on the direction of movement, and it is moving to the right. So that's going to be the positive direction. So that gives me Tx plus minus the frictional force will be equal to m times a. And when we substitute that, that is 16,96 times cos of 15 minus the frictional force that we're looking for, and that will be equal to 8 times 1,32. And then we just have to solve for that kinetic friction, and you end up with 5,82 Newton. Now they tell you that that 8-kilogram block moves from B to C, and as it moves from B to C, they say the kinetic frictional force between the block and the surface is not constant, and then they ask us for a reason for that. Now, as you move from B to C, when you get to number C over there, you will see that the angle between that rope and the horizontal, that angle is increasing. When we want to talk about kinetic frictional force, remember kinetic frictional force, you would have worked that out with mu k times the normal force. And that mu over there is determined by the smoothness of the surface. Now, in this instance, they changed only the angle there. They did not change the surface. So mu is going to be a constant. So I need to think about the normal force. In this situation, N is going to be smaller than the gravity because you've got the y component helping it to keep it from sinking into that table. So here you will have N equals to gravity minus that y component. And what happens when you've got the y component? Now with the y component, that will be the whole t times sine of that angle. Now, if the angle increases, it means that sine of that angle is also increasing. Sine always does the same as the angle. And that tells me that that y component is going to be bigger. But you get the normal force from gravity minus the y component. So if you've got a bigger y component, that tells me that my normal force is now going to be smaller. And if my normal force is smaller over there, that tells me that my kinetic frictional force is going to be smaller. Now, in this last question, 2.5, they tell us that the horizontal surface on which the block is moved is replaced. So they are taking that surface and they are replacing that with something of a different material. And now they ask, will the kinetic frictional force calculated in the above change? And the answer is a definitely yes, because mu k depends on the surface. Now, in this last question from 2019, they tell us that a block of mass 2 kilograms connected to Q, mass of 3 kilograms by a light inextensible string. Both blocks are on the plane inclined at an angle of 30 degrees to the horizontal, and that is in our diagram. Q is pulled by a constant force of 40 Newton at an angle of 25. This is a little bit new, right? And now P moves on a rough section. So over here we've got gravity, and while Q moves on a frictionless section of the incline. See the diagram below. So everything is in there, and then they tell you that the average constant frictional force is 2,5 Newton that acts on P as it moves. Now the first question here is to draw a labeled free body diagram for P. Now, if I look at P, there's the tension in the rope. Remember, a rope is pulling on both sides with exactly the same amount. So if it's pulling upwards at number P, it's pulling down at number Q. So for P, that will be an upward force, and for Q, that would have been down. And then we also have a normal force. So there's a normal force perpendicular to that. We have a gravitational force. So the gravity we can split up into a parallel and a perpendicular component there. So that was the answer for 2.2. And then in 2.3, they ask us to calculate the magnitude of the acceleration of block P while it is moving on the section AB. So we are looking for acceleration and we only need the magnitude. Now, acceleration, the moment that you see acceleration, that's going to tell you that we are working with Newton's second law. And then F net is not zero. So now we're going to start with F net equals m times a, but very important, you have to do that for every object separately. If you do this for the combined system, you will get the right answer, but you'll only get 5 out of the possible 8 marks. So let's go and draw the free body diagram for Q first. So for Q, the tension is a downward force, and we've got the normal force. Then we've got gravity. And then we also have that applied force. And that applied force, we can also now split up that applied force into a parallel and into a perpendicular component. Right, so now we're going to do Newton's second law and apply it to every object separately. So if you look at them, it's going to be F net equal to m times a for P, and also F net equals m times a for Q. So let's look at P first. P, that is a 2 kilogram object, and we need the acceleration. So that's an unknown. And now we look at the forces, the net force. Remember, we don't need to look at the perpendicular one. That's going to cancel out. We only need to look at the direction of movement, and upward is our positive. So here it would have been T plus minus. So it's T minus the friction minus the gravitational parallel component, and then we just have to substitute. And then we end up with T being 12,3 plus 2a. Let's do the same for Q. Now here, once again, I don't have to worry about the perpendicular direction. I'm only going to focus on the direction of movement, and upwards is going to be my positive direction. So here, this is going to be F parallel plus minus T plus minus FG parallel equal to M times A. We want that parallel component, and in that diagram, this is the adjacent to that angle, and this is the hypotenuse, and therefore we're going to work with cos. And then we rewrite to get T, and that is equal to 21,55 minus 3a. Now remember, the T's are not the same force because they are definitely in different directions, but the T that we have over here is not standing for the whole force. We've already put the minus and the plus in there to indicate direction. The T we're left with over here is just the magnitude, and the magnitude of those two are exactly the same. So we can say 12,3 plus 2a is exactly equal to 21,55 minus 3a. And then it's just a question of solving for a, and we end up with an a of 1,85, and that is meters per second square.